You open your Class 10 science exam, and staring back at you is a nightmare of zigzag lines, circles, and batteries. It is the classic, highly complex electric circuit diagram. The panic usually sets in right here. You look at the maze of wires and realize you have no idea where the electrical current is dividing, which components are connected in series, and which are sitting in parallel. Navigating this maze becomes possible once you identify the relationship between three distinct characters. First, the pusher, then the flow, and the blocker. Mastering circuit diagrams requires no rote memorization. It is simply about learning to read the hidden, strict logic of how electrons navigate a path. Electrical charges, specifically electrons, do not move through a wire on their own. They require a push from a battery or cell to get going. This push is what we call potential difference, or voltage. Once that push is applied, charges move. The actual rate of flow of these positive charges rushing through a conductor is called electric current. But the wire isn't an empty highway. Electrons bump into the metal atoms as they travel. This creates a natural friction that opposes the flow of the current, known as resistance. This brings us to Ohm's law, written as V equals I times R. If you apply a bigger push, you get more flow, but that flow is always strictly limited by the resistance, acting as a bottleneck in the wire. While Ohm's law dictates the math, how you actually use that equation completely changes depending on the physical shape of the wire's path. When components are connected end to end, forming a single undivided road, we call it a series combination. Because there's only one path, the exact same current flows through every single component, but the total voltage from the battery gets divided among them. The fatal flaw here is the dependency. If a single filament snaps and breaks the path, the entire system immediately goes dark. A parallel combination offers an alternative. The main circuit splits into multiple branching lanes. Here, the current divides to take different paths, but each individual lane receives the full undivided voltage directly from the source. Because each branch operates independently, one broken bulb won't affect the others. That independence is exactly why domestic household wiring uses parallel circuits. This snippet shows calculations to find equivalent resistance. As seen in Case 2, for series resistors, you simply add their values together. But for parallel branches, shown in Case 1, you add their reciprocals, making the total resistance lower than the smallest individual resistor. To solve any circuit, you just need to trace the wire with your finger. If your finger never leaves the line, it is series. If the road splits into multiple paths, it is parallel. When electricity struggles moving through a wire with high friction, that kinetic energy doesn't just disappear. According to Joule's law of heating, it converts directly into extreme heat. We harness this heat daily. Heater coils glow red, vintage bulbs emit bright light, and safety fuses intentionally melt before your house catches fire. This equation block shows how we measure electric power, which is the exact rate at which this electrical energy is consumed. Power equals voltage multiplied by current, which can also be calculated as voltage squared divided by resistance. These calculations go far beyond the exam room. When you multiply that power by time, you get the kilowatt hour. That is the exact unit the electric company uses to measure your energy consumption and calculate your monthly bill. Returning to that initial circuit diagram, we can now see a sequence of solvable steps rather than an overwhelming mess. The first step is to locate where the current splits. We identify the parallel branches, calculate their equivalent resistance by adding their reciprocals, and physically merge them into a single, simplified resistor block. Now, the path is just one single road. We simply add up the remaining series blocks to find the total equivalent resistance of the entire circuit. With the total resistance calculated and the battery's voltage already known, we apply Ohm's law one last time. Dividing the total voltage by the total resistance instantly reveals the total current flowing out of the battery. Electricity operates entirely on a strict logical flow. Once you learn to trace the path and apply the rules of the flow, you master the exam, and you understand the science powering your own home.